Briggs for another episode of Uncertainty and Probability Theory, the Logic of Science. We're on episode 64, no confidence interval in parameters. Double joke there, stupid pun, interval, get it? Well, we talked about, we're still on hypothesis testing and why one should not engage in hypothesis testing in any of the usual senses. Of course, what we really want to know, what we always want to know, as I tell us, is the probability of some hypothesis, whatever it might be, some practical question, some impractical question, whatever it is, some proposition that you have about the world, you want to know if it's true, or what probability is true given whatever evidence that you're willing to consider. You change the evidence, in any way whatsoever, you change the model that you're considering of the thing, you change parameters in the model of the thing that you're trying to consider, you change anything, you take more data, you subtract some data, you do anything, you change the evidence, you change the probability. This is not a bug, it is a feature, it is the way probability ought to work, it is the way probability in fact does work. If your evidence changes, of course, your view about the proposition of interest ought to change. Meanwhile, what we get instead of this is we get the probability of data we did not see, given that the hypothesis is false. That's this is the p-value, and people use this when it's we equals some kind of we thing here, when it means it's less than the magic number. They use that to infer, without stating a probability, that the probability of this is high or even certain. They want us to say the probability of that is 1. In fact, that's the decision that is made. The confusion is when this thing is small, we decide, we reject this null hypothesis, which means we accept this other hypothesis here, the logical contrary of whatever this is. Now, this is nuts. There's absolutely no reason to do this at all. It's useless. It doesn't answer any question we want to answer. This is the question we want to answer. Why don't we do that? Well, we're going to see how we do that. But sometimes people say, you know what, I don't want to use this p-value either, so I'm going to use parameters. I'm going to parameterize these probability models. Now, we ran into parameters many times, and we talked about the origin of parameters and how I think this is a brilliant area for research to show how in finite discrete situations, the evidence that we have can be taken to a limit in some way, in some mathematical way that is plausible under the circumstances that you dictate. And that comes to a probability model that is where the parameters themselves reside on the continuum, where the probability model resides on the continuum, which in the limit are always useful approximations, and that's what we're going to see today. Useful approximations. The math is a lot easier when you're on the continuum with these things, all that kind of thing. There's absolutely nothing wrong with doing that. I want to insist on that and emphasize that. There's nothing wrong with using these probability models, but always keeping in mind they are, in fact, approximations. And useful approximations at that. But as long as we keep that in mind, we won't make these logical mistakes, which, of course, as you can guess, today, we're not going to keep in mind. So we want to first talk about how parameters are used in these hypotheses and show you how that fails. And then we're going to look at one of the attempts to escape this kind of a thing, which turns out to be equivalent to this kind of a thing, and that's confidence intervals. Confidence intervals are yet another instance in which nobody acts as the theory says. The theory states, definitively, positively, frequentist theory states, you must interpret confidence intervals in this way, and there's no other possibility. That's what the theory states. Absolutely nobody treats confidence intervals in that way, and they instead treat them in a Bayesian way, and almost getting to something like this. And I'm going to show that to you. I'm going to prove that to you. Okay, so let's suppose, again, we have some like I think I used the example weight loss. Weight loss drugs are currently the rage. Instead of people eating less, they want to eat as much as they like and take a drug to help them lose weight. And so suppose the manufacturer of these drugs is interested in whether or not the drug affects men and women differently. All right, that's a legitimate question for them to answer. Women probably want these drugs more than men, and they want to know, we can even put this in proportional terms because women are on average lighter than men. You're not supposed to hold with reality like that in this day and age, but that's the case. So we can put this in relative terms or absolute terms, whatever terms we want. It doesn't make any difference. There's so far no difference between this hypothesis testing way and the way, the questions we want to answer. Those are stated in the right way. So what will happen is we'll have some kind of a model. We'll have some data we collect on this in one way or another, some evidence that we take in, and everything that we're going to consider. Almost always at this point we introduce an ad hoc model. We don't consider how the data is collected. We can only measure weight loss to a finite and discrete level, no matter what. It could be very, the detail can be very fine. The number of divisions that our scale happens to be can be have a lot of gradations to them. All true, but no matter what, we can only measure any kind of weight loss or weight gain or weight of any kind to a finite and discrete way. Now, it would be very nice if we had the finite and discrete model for weight loss, one for men and one for women, under the circumstances in which we're considering. But that would be a very complex model. We'll look at some of these kind of things as we do more and more models. We're going to get into all these models deeply. But as a reasonable approximation to that, we might use one of these things. We might say, here's the finite and discrete way of mapping out all the measures I might take and the decisions I want to make with this kind of a thing at the level at which I want to make them. And then off we go using some sort of continuous approximation. That's fine if we did that. Almost never is that done. And instead, we just plop down an ad hoc model. So what will be done instead is usually, in cases like this, I don't say always, I say usually, in fact, mostly. We'll have a normal model in which we'll have this particular parameterization. And I'll say men here. The normal has a parameterization such we need to specify the central portion of the normal, and we need to specify the spread of the normal right here. Here's going to be 0, and this will be in pounds, if you like. And basically, this model says, whatever this value is, doesn't matter. For the moment, we don't know what this is, some sigma squared. Remember, we write these in Greek letters when we specify they're on the continuum, just custom. It's a reasonable custom. And this is the central locus. We don't want to say the mean of the normal distribution. That's a mistake everybody says. It's not the mean of the normal distribution, it's the center point of the normal distribution. The mean is just any number you take together, add a bunch of the numbers together, n of them, and then divide by n. That's the mean. That doesn't have to equal this, but that comes out to be the approximation of this. This model says something like this. This here, in the first approximation, we don't have to let this be the same for men and women. We don't have any kind of indicator function to change this for men and women. Almost always it's not done. Why? Because of tradition, because of ease, because of custom, not because there's any logic to it usually. We could let this have another indicator function in here. We could have a sigma squared 0 plus an indicator sigma 2 squared sigma 0, sigma 1 squared indicator for men. We could have something like that in here too. That's done. This kind of thing is done, but very rarely. So for now, we're not going to do that. We're going to assume they're the same. So if I draw this correctly, which of course I probably won't, the idea is we're going to say women will lose more than men. We'll draw women in this. I should draw women in blue, but blue doesn't come up very well here. These should have the same shape. but just one is shifted one way or another. Now, this is, of course, all probability is a matter of the mind. This is how we'd want to think about it. We'd want to say if this is weight loss and here is 0, this is positive. Well, I guess this is weight gain, if we'll think of it this way, and this is weight loss over here. I could have done this opposite where the positive was weight loss, but I didn't, like an idiot, so it doesn't make any difference. It's just a sign flip. So here's one and here's the other. That's what this model is right here. All right, and that's a model of our thinking about the weight loss. That's not what happens in reality. In reality, people lose weight by a cause. That cause could be the drug. That cause could be any number of other things. We're not tracking every single possible cause in these things. We're not even, and sex isn't even a cause per se. A person's sex doesn't make them lose more or less weight. It's what happens inside their body because of their sex that makes them lose weight. So sex isn't even a cause. It's a proxy for other types of causes inside the body. So this is not a causal model. It's often interpreted as a causal model. And the null hypothesis here, remember we have to have a hypothesis here. The hypothesis we want is that beta 1 does not equal 0. That's our hypothesis. That's classically the hypothesis. And the logical contrary of that is that beta 1 does equal 0. If beta 1 equals 0, then we just have whatever that might be. Oops. Some probability that likes like that. That's a model of our thought of our epistemology of the situation of weight loss. If beta 1 equals 0. If that's our so-called null hypothesis right there. Now, I'll put quotation marks around that kind of a thing. People will say, you know what, we want to know the true value, I'll put that in scare quotes too, the true value, holy moly, I'm already running out of time, of beta 1. Beta 1 doesn't have a true value. There is no true value of beta 1. It doesn't exist. For one thing, this is a normal distribution. Normal distributions give positive probability, however small, for any number all the way out to infinity and all the way out to negative infinity. That's impossible in man, in the species man. So this is not, there is no true value. There is no true value. I cannot emphasize that enough. You can posit an infinite sequence, which you have to do, an infinite sequence of men, if you want to be strictly frequentist, an infinite sequence of men and women, and repeating this experiment an infinite number of times, which you have to do for confidence intervals, as we'll see. But that does not mean that there's going to be a true value. Even if you had an infinite number of people and you got the whole population, probability is not causative. This language is probability is causative, that probability is real, that it's inherent, that nature is drawing. You'll hear people, nature is drawing numbers from a normal distribution. Nature is doing no such thing. Nature is built up of all these causes, of all these substances operating using their powers under whatever conditions they have and so forth. So this is nothing but a matter of our thought, but this is treated as if it's a real thing. There is no true value of this beta. It's just something that we're using to see if how our probability changes in these things, in this particular outcome. All right, but now notice that this is a very complex and weird. Look, this is absolutely fine logically. This being our hypothesis that beta 1 does not equal 0. And the null hypothesis that beta 1, the logical contrary, is that it is exactly equal to 0. There's no problem logically with this. And in fact, we did last week, it must be that beta 2, you know, the sock color of green. We take beta 2 based on other evidence to be precisely exactly 0. And an infinite number of other hypotheses that we're adding to these things we take to be exactly 0. So there's no problem with that. There's absolutely no problem with that. But this is not a very informative hypothesis that beta 1 does not equal 0, because of course beta 1 could equal 0.000000 1, which is, if we're talking pounds, probably not of most interest to most people. It could equal, beta 1 could equal 83 million, the true value could be. That's any one of these things here, any one of these type of propositions are consonant, logically consonant with this hypothesis. So what we have here is an infinity of hypotheses here that we're saying is true. One of them must be true, but we're not saying which one can be true. All right, we have not given any indication which one of these things, out of the infinite number of these, beta 1 could go, 10 to the 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 10, 100 times. That's a hypothesis that's logically consonant with this, right? So we're not giving any indication which of those are true. So hypothesis testing says we're going to either reject this, which means we're going to conclude this is true, which is useless because there's still an infinite number of these that we could pick. But then they'll say, if B1, if we're rejecting this, then the weight loss drug must have caused the difference between men and women. That's not true. We bring cause to these models. If we say the only possible cause, if we come to the model and say the only possible difference between men and women is causal because of all those factors that might be causally related to sex, then we brought that to the model and we rejected this that says that's true. In other words, we first assumed it's true, and then we reject this opposite of it, and we conclude it's true. We can't then say the data confirmed our causal surmise was true, because that's the surmise we brought to the data. We said this was the possible cause, and we gave no other possibilities for the causes for this weight loss difference between men and women. There could be anything, right? There could be absolutely any. In reality, there could be any number of causes that were responsible for the results that we had seen. The men are all, from Harvard or something like this, very, anemic and weak and, pathetic, pitiable creatures. And the women could have all been from, from northern Michigan or something, not having anything to do with any university, just ladies who work out and robustly work out on the farm and in nature and things like this. So the differences that you have between the groups might not have anything to do with sex per se at all. We don't know that in this kind of a thing because we only surmise it's either sex caused this, which sex can't cause anything, or it didn't. That's it. So that whole idea of hypothesis testing to affirm a cause is false because we're the ones who bring cause to the model. So the next problem to try to solve is, well, I got to somehow get at this because I don't know what any one of these particular hypotheses are that beta 1 could be. All I said, it's going to be one of these, and there's an infinite number of them. We got to narrow that down if we want to have any kind of a useful model. Hence, enter confidence. Now, this particular thing about parameters, this complaint that I'm making to you, applies not just to this kind of a normal model, but to any model. Absolutely any model in which you're using these continuous parameters as in probability, which don't exist. They're all matters of your mind. You change you're the one who came up with this ad hoc representation in the first place. So, this is all just a matter which we can absolutely do to make our probabilities work. But it doesn't mean this is existing in nature. And in fact, it cannot. We know by other evidence that men and women cannot gain or lose infinite numbers of pounds or anything close to even thousands of pounds. Let's say 10,000 pounds, anything like that. We know is out of bounds no matter what. So this model cannot be true. There cannot be true values. Any normal model can never be true because there's nothing infinite in the universe, and so forth. So we did all that kind of stuff before. But we still want to narrow this down. So let's talk about confidence intervals. Let me erase. I have to erase all this kind of stuff right here. So I want to talk about confidence. Oh, I should have kept that. But I think you'll remember. I think you'll remember what the beta 1 was. There's a thing called a confidence interval. So let's talk about this. Here again, here is 0, and here is our beta 1 axis right here. Now, for this particular data, I'm not going to calculate it for you. Software will do it for us. We don't care about the exact value of the calculation. But here is the confidence interval right here. This is called, usually we use a magic number confidence interval. It's no surprise this is 95%. It's 1 minus the magic number 0.05%. It's the same thing. And the idea is, if 0 is inside this confidence interval, we cannot reject, fail to reject beta 1, the null hypothesis equals 0. In other words, HF. We cannot reject this null hypothesis. So it's exactly the same as a p-value, used in exactly the same way. But now let's talk about the interpretation of the confidence interval. Let's suppose, in fact, our confidence interval wasn't like this, and it was something like this, right here. Now, this is not, 0 is not part of this 95% confidence interval, and therefore we reject beta 1 equals 0. In other words, we accept that beta 1 does not equal 0. So now, here is our confidence interval we calculated for this, about this parameter right here. What's the interpretation of this confidence interval? I'm going to tell you. You're going to forget, as absolutely everybody without exception forgets, but I'm going to give it to you. Now, this is frequentism. This is the logic and rule of law of frequentism. You have to follow it exactly. Now, this particular experiment that we did, in order to calculate this, it's just a calculation you do. It gives you a confidence interval around this parameter. The actual calculation is not of interest to us. Any bit of software will do it. We gathered some data, okay? It's just some function of the data we gathered, x1, x2, xn. We have n of them. It's just a function of that. That's all that, it's just a function of these things right here. And that's all we have to know about these kind of things. There's the additional information that we have a size n of these, okay? Now this is frequentism. We did an experiment, we got this thing. This, we have to keep in mind, this is ours. This is the one we got. This is the one we have right here, ours. Now, frequentism demands that the experiment that gave rise to this is embeddable in an infinite sequence of experiments. Each identical, except, in other words, you give the same drug, the same men and women, that kind of a thing. They're identical to the first batch, except randomly different, where randomly is never specified. Randomly different. There's no thing in logic that comes to this. There's lots of proposals for meaning for this randomly different, but none of them are hold any weight. If the same causes are operating, the same exact causes, then those causes would be the same in the next group of people. And if those causes are not the same, then they're not the same, and then we're not measuring the same thing. So this randomly different stuff doesn't mean anything. But let's just suppose we can repeat the experiment again. And we again take n. It has to be n, can't be n minus 1, can't be n plus 1. But we imagine we do this. We get n plus 1. Now, what I'm going to do, well, I'll do circles on the ends of these. How about this? That's experiment number 2. Experiment number 2. If I were to imagine redoing this experiment and I calculated n people again, and I put it into this formula, the confidence interval formula, I might get something like this. It's possible, right? And then I could do it again. I could do, here's E3, and here, over here, is E4, and here, I don't know, is E5, and here is E6, and so on. How many do we have to do with these? We have to go all the way up to infinity. Okay, we have to imagine we could do these experiments and we can repeat them. We've got to embed this in an infinite sequence. That's what frequentism is. This thing is embedded in an infinite sequence. There's no other interpretation of this. All right, so now we got, what is this? I didn't even know what I did there. So we have this as experiment 6. Now, here's the interpretation of a confidence interval. Are you ready? I don't even know what that is I hear. This is the, like I told you, it's summer, and it's the sound of lawn work on everybody's doing their lawn work every day of the summer, which it's not raining. Anyway, so here's the interpretation of the confidence interval. Here's ours. We see it. It has specific values. We see it's less than 0. They're all the 95% confidence intervals. It doesn't matter. The exact number here doesn't matter, just like the exact number of the p-value doesn't matter. It's whatever it is. It is this. Here it is. Pay attention. 95% of these, 95% of all of these, 95% of all repetition CIs will cover or contain, if you like, the true value of beta 1. 95% of these, 95, some of them won't. 5% of them won't. 95% of them will cover the true value of beta 1. There's two things immediately wrong with this. The first is there is no true value of beta 1. It doesn't exist. Doesn't exist. We've already ascertained that from other evidence. So that's part's wrong. But if we can pass that by and say, well, we're vaguely thinking about approximations here, so we're going to just not think about that particular problem. All right, we'll let it pass. This says 95% of every one of these confidence intervals in the infinite set, not large, not 10 or 20 or 100 or 1,000 or 10,000, an infinite set will cover the true value. What about ours? What can we say about ours? Because we're not going to do these experiments. We haven't done them. All we've done is this. This is the only evidence we have. What can we say about this? This. It's very important. It's very important. Our interval, our CI, covers, or contains, whichever word you like, V1 or not. Aha! Isn't that deep? Our confidence interval either contains beta 1 or it doesn't, and that's all we can say. I promise you this is true. I promise you nobody likes it. I promise you nobody remembers it, but that's all you're allowed to say. Our particular, you can't say it has a probability because you can't put probabilities on parameters. So here is a confidence interval that goes out here that I can calculate for this particular problem, going out to tens of thousands of pounds this way, tens of thousands of negative pounds this way. This interval either contains the true value of beta 1 or it doesn't. This interval contains the true value of beta 1 or it doesn't. This interval contains the true value of beta 1 or it doesn't. This contains, and so on and so forth. You're not allowed to put any kind of probability measure on parameters. But here's where everybody then all of a sudden says, you know what? I think this one's pretty good. I think the beta 1 must be within this window right here. You can't say it has a 95% chance of being in there. That's Bayesian. You can't say it's a 95% chance of being in there, or even any kind of a chance. You might try to flub, but not use exact probabilities, 95%. You'll say, oh, it's a large chance that beta 1 is in there. You can't say that. Just because you're pretending not to put a number to it doesn't mean you haven't used probability where it's not allowed. You're not allowed to put probabilities to any of these statements. It's just forbidden, but everybody does. And here's the next thing they do. If you have two confidence intervals, here's our beta 1 here. If you have two confidence intervals, people will say there's roughly a 95% chance that beta is in this little interval here, and there's a 95% chance that beta is in this wider interval up here. They'll say this one is tighter, and therefore we could be more sure or surer that beta 1, the value of beta 1 than we can of the beta 1 in this one. No, we can't. If we're more sure about the value of beta 1 here, that means we put probability to it, which is forbidden. You're not allowed to use probability for these parameters. So absolutely everybody does this though. Everybody says when the confidence interval's tight, when it doesn't contain zero, they're pretty confident the true value of beta 1 is whatever the interval they have there by whatever confidence they've used. All forbidden statements, but yet every single person makes them, without exception. None. No exceptions. You'll see in every time a researcher uses these confidence intervals as a replacement for p-values, he's just done p-values again, but adding a little bit extra information. So the point of it is, he interprets these things as a Bayesian does. He interprets these parameters as they can accept probabilities. Now, if you're going to give probabilities to values of parameters, why not just give probabilities to values of parameters? Or even better still, as we'll learn, why not just forget about the parameters altogether and give probability to the observables themselves, which is the very question you want to know. Are men and women different in the weight loss? That's what we want to know. Or we can ask any kind of question we like. Are men going to lose twice as much weight as women? Or only half as much weight as women, or whatever we want to ask, we can ask. We could do that using regular probability, but you cannot do it with confidence intervals because absolutely everybody gets them wrong. They're all wrong. Absolutely everybody treats them as a Bayesian, and if they're already going that way and they're giving these things probabilities, why not just go all the way to Bayesian? And if you're going all the way to Bayesian, why not just go all the way to logical probability and answer the question that you really wanted to know? That's what we're going to do. We have reached the end of hypothesis testing. We're going to meet it. I know I've run over time here, but we're going to meet it many times in all the models we're going to look at. Now we're going to look at real models. The one I erased up there, that was called regression. We're going to look at regression in depth. We're going to look at all kind of models. We're going to look at it's done the wrong way, the frequentist way, hypothesis test way, the Bayesian way, which is semi-right, and we're going to look at the logical way, which is correct. We're going to do all that and do lots and lots of models, and we'll get them from Jaynes and all that kind of too. I know I've been neglecting Jaynes because I wanted to get this philosophy stuff done. I know I've gone over time, but that's it for now. I promise you, look at absolutely any use of confidence intervals or p-values, and you'll see every rule I said can't be broken will be broken. Nobody is a consistent frequentist, not one person. All right, that's it for now. Thank you very much for listening.